Oh, welcome to my talk. The title is Regional Correlation Detection for Seismic Events in Mongolia. My co-authors are Paul Richards, Jocelyn Lopez Luna, and Yaron Ekstrom. The big picture is we're monitoring seismic events is important for both underground nuclear tests and atmospheric or oceanic explosions as a component of nuclear monitoring with complementary and independent information to infrasound and nuclear isotopes. Motivation is improving detection, location, and identification for seismic events and nuclear monitoring using regional stations in the International Monitoring System arrays. This work relates to the NNSA mission because of the importance of being able to monitor for nuclear testing to help prevent developing nuclear weapons. The technical approach is to use about 1,000 master templates from the Late Event Bulletin, the LEB, at 2 or more stations, and continuous data for 5 years from 2012 to 2016 on a sparse network of IMS arrays and 3 component stations, shown in the left with red triangles. We select templates within the green polygon from the events in black that are seismic events in the LEB. And then we do correlation detection and obtain a catalog that we verify at 2 or more stations in a detected catalog. And then we want to do locations. To do a location, we need 4 stations to get an epicenter location and origin time and error estimates. So fortunately, we were able to use a sparse regional temporary deployment for Mongolia that Lehigh University deployed in a dense network in Kyrgyzstan, shown in the right, that we were able to get correlation measurements for events that we tried to locate at 4 or more stations. It saves computation time to detect on continuous data streams with a sparser network, and then for locations, use a denser network of stations using windowed data. The result is that we have about 33,000 events that we detect using the master templates of about 1,000. So that's 33 times as many detected events, and then we locate them in cluster locations. And it's shown in the table here compared to previous work that we did for all of China and the Wenshan aftershocks in China. And what we have is about 420 meter mean errors, 95% confidence ellipses for all of China, 370 meter errors for Wenshan, and 280 meter error for Mongolia. The improvement in the residuals from the starting locations to the final locations for all of China is improved by a factor of about 89 times. And for Wenshan and Mongolia, which are detected events that we assign to the master locations, the improvement is about 32 times for Wenshan and 33 times for Mongolia. So similar improvements for detected catalogs. And that's to be expected because there's less scatter in the detected catalogs when we assign the detected events to the master events that detect them nearby. We look at the detected catalog for the events in the clusters and do time of day plots in local time on a 24-hour day and day of week plots. And here we show 11 large clusters with hundreds of events that we can identify as man-made because they occur during the working hours from 9 a.m. through 5 p.m. These 11 clusters have 91% or more of their events occurring during those times, which are shown by the green lines. There is an aftershock sequence on the left that shows random behavior throughout the day that is more characteristic of earthquakes and not man-made explosions. The day-of-week plots show Sunday is the first day of the week, Saturday is the seventh day of the week, and 8 clusters have 30% or less events on weekends. And the aftershocks in the corresponding plot show a larger number of events on weekends. Time of day estimates for random uniform origin times would be about 37.5% of the events would occur from 9 a.m. through 5 p.m. And what we have is 94% of the clusters with 30 or more events have 70% or more of their events occur from 9 a.m. through 5 p.m. 84% of clusters with 30 or more events have 90% or more events occur during working hours. And 74% of clusters with 30 or more events have 98% or more of their events occur during working hours. This represents the first 50 clusters and 31,000 events out of 316 clusters, or 16% of the clusters and 96% of the 32,000 events in their catalog that is detected. And for clusters with 4 or more events, we see similar things, but with less statistical significance, that most of the events occur during working hours. And this represents the first 142 clusters, or the 45% of the clusters and 99% of the events. About 31,800 events belong to a cluster with 4 or more events, and 75% or more of the events occur in those from 9 a.m. through 5 p.m. So possibly 97% of these events are man-made just based on time of day analysis and more detected events that we measure in a cluster. From that previous analysis, we plot here on a map blue circles with clusters with 4 or more events in a cluster and 75% or more from 9 a.m. through 5 p.m. that we might expect them to be classified as man-made. Cyan circles are clusters with 3 or less events in a cluster, or less than 75% from 9 a.m. that we might classify as being earthquakes. And red stars are the largest clusters with 30 or more events occurring during working hours. And you see that they occur distributed throughout the area and associated in regions with large mining activity in Russia. Here's a plot of absolute locations in the LEB on top in the top panels, and relative LG correlation locations in the bottom panels for the same events in both plots. And the map axes are the same scale. So we see a great reduction in scatter in the locations from the absolute to the relative using the correlation measurements. And taking the differences between the locations, we have a dislocation of about 15 kilometers in both cases. The 95% confidence relative location errors are less than a kilometer here. And these are 2 of the largest clusters. If we take the clusters in the centroid of the cluster locations and compare them to satellite imagery, we find that they correspond to surface mines. Here's 2 examples, with one with green vegetation and brown surface mines, and the mean cluster absolute location in red plots right on top of the mine. Another cluster with lighter areas that are surface mines with the mean cluster absolute location plotting right on top of the mine. It gives a good absolute location. The expected impact is a possible reduction in detection threshold by 1 magnitude unit in areas with similar events, high resolution locations, 1 to 2 orders of magnitude improvement, characterizing events as explosions or earthquakes with independent complementary information, automated processing and real-time systems, and a correlation event screener for many earthquakes and aftershock sequences at swamp monitoring systems. The MTV impact would help students in participation in workshops. Our collaboration is mostly with Sandia National Laboratories, and anyone interested in nuclear monitoring or monitoring in general would benefit from this technology. And our conclusions are from about 1,000 master templates, we detect about 33 times as many events in 5 years in the area. The sparse regional subset of stations can be used for a detected catalog verified at 2 or more stations to save computation time. For high resolution locations, window data on denser network of stations can be used. 95% confidence ellipses have averaged 280 meter semi-major axes. And reduction in residuals, it's a 33 times improvement from the starting locations. Many large clusters at mines have 97% or more of their events occur from 9 a.m. through 5 p.m. working hours local time. Many of these mining clusters also have 30% or less events on the weekends. 97% of the events are man-made just based on time of day analysis. And more detected events in a cluster. Comparison of absolute LEB locations to relative LG locations has an average mean mislocation scatter of 14.5 kilometers and a maximum of 46 kilometers. In comparison of mean absolute centroid locations of clusters shows 9 out of 14 largest man-made clusters can be associated with surface mines, sometimes plotting right on top of the mine, and in other cases from 1 kilometer up to 15 kilometer mislocation bias. Next steps, we'd like to apply it on a broader scale to other regions of interest, see what improvements can be made in absolute locations with seismic measurements, and study more detailed satellite imagery for absolute locations and ground truth. Thank you.